everybody. Welcome to our next video. We're going to be talking about hydrates. And this is kind of in follow-up to our percent composition and our empirical formula lessons that we've done, because hydrates will encompass both of those. All right, so when you think of the word hydrate, hopefully you think of water or hydration, and that's exactly what you should think of. When we're talking about a hydrate, we're talking about an ionic compound with a specific number of water molecules bound within the crystal structure of the solid. Now let's break that down a little. It's an ionic compound, meaning there's a metal in it, metal and nonmetal bonded together. We call this ionic compound the anhydrous, okay? It has a specific number of water molecules bonded to it. This is where the hydrate comes from, okay? These water molecules we call the water of hydration, right? And they are bound, not bonded. So this is not a chemical reaction or chemical bond, at least in the kind of hydrates, the inorganic hydrates that we're going to be looking at. So that means there's no carbon in them. Therefore, the water is not bound, or it is not bonded. It is bound, just absorbed, into the crystal structure of the solid. Now, we can take a hydrate and we can evaporate the water to make an anhydrous, just the dry ingredients. Or we can take an anhydrous, which is the hydrate minus the water, and we can rehydrate it to make a hydrate again. So it's a back and forth thing that we'll actually be doing in our lab next class. All right, so a hydrate we can name. It's very simple. We name the ionic compound of it the same that we would, or that we learned to do already, right? So just name the ionic compound, and then for the hydrate part, you name that part prefix plus the hydrate. Okay, so let's look at an example. Over here, right here, our example, BaOH2 dot 8H2O. Now, this dot is not a multiplication sign. This dot is telling us that the water is not chemically reacting with its barium hydroxide, but it is absorbed into the structure, okay? So this is the entire hydrate, BaOH2 dot 8H2O. Now, how do we name that over there? BaOH2, hopefully you remember, barium hydroxide. Okay, so barium hydroxide. This is our hydrate, so we just need to know the prefix for 8. And we get that from the back of our periodic table, right? We saw those with molecular compounds. And we find 8, and we say that this is barium hydroxide octahydrate. The octa is for 8. Okay? So pretty simple naming. The other two things that we can look at here are percent mass the molar mass and the percent composition. Now, the molar mass for barium hydroxide is just like we've been calculating molar mass already. So I'm not showing you how to do that. I've put it here, 171.35 grams per mole. The molar mass of the 8H2O, the water of hydration, we have 8 times the molar mass of water. And you get 144.16 grams per mole, okay? So this is the mass of the part barium hydroxide. This is the mass of the part water of hydration. And here's the mass of the whole, 171.35 plus 144.16. The total is 315.51 grams per mole. From this information, you should hopefully see that it's very simple to calculate the percent composition. We have a part and a whole. A part and a whole, okay? So when we look at percent composition, we look at percent composition for just these two pieces. We're not breaking up Ba, O, and H, all right? We're looking at the percent composition of barium hydroxide and the percent composition of our water of hydration. So I've done that down here for you. The part for barium hydroxide is the molar mass of barium hydroxide, 171.35. The whole is this total. So I've put the total on the bottom. Multiply it by 100, and you see that our grams per mole crosses out, and we're left with 54.309% barium hydroxide. Over there, the part, which is the water of hydration molar mass, divided by the whole, times 100, and in the pink box over there, you get 45.691% H2O. Okay? Again, you don't need to break it down into each individual element when we're dealing with hydrates. Right? So let's take a look at what we're actually going to be seeing in the lab. all right, when we go to calculate information in the lab.
Okay, so this is all data that we are going to be collecting in the lab, but we gave some to give you here just so we can use it to go ahead and figure out the percent composition of the hydrate and then actually figure out what how much water we actually have in it. So a hydrate of sodium sulfate has the formula Na2SO4, that's sodium sulfate, dot our water. And we have an X here because we are going to solve for how many water molecules we actually have within this hydrate when it is hydrated. So the first thing that we need to do is calculate the masses of the hydrate, the anhydrous, and the water. Now we have we have some data related to that, but I just want to remind you all how we're going to just do a little bit of subtraction to figure out exactly what the mass of the hydrate is. So we have the mass of our crucible at 12.10 grams, and we have to subtract that from the mass of our hydrate and our anhydrous to figure out what the mass of those two things. So for our hydrate, we have the mass of the crucible and the hydrate, 18.51, minus the mass of the crucible, and that gives us the mass of just the hydrate. And we end up with 6.41 grams.
Do you want to explain what crucible is?
Oh, right.
I forgot.
My bad. So the crucible, we should have brought one of those. A crucible is like this little tiny ceramic cup, and that's what we use. We put it on top of above our Bunsen burner, and it can absorb a lot of heat, and it heats up our hydrate and evaporates all the water out of it. So and it has a little baby top. It's very cute. It's like we're having a little tea party in class. Okay, that's a crucible. So, my bad, yes. Anhydrous. To calculate that, we're going to take the mass of the crucible and the anhydrous, this is after we've done all the heating, we've evaporated all the water, it's just going to have our sodium sulfate left in it, minus the mass of the crucible to give us our mass of our anhydrous, which is 2.83 grams. Now, to find out how much water was actually in there, all we have to do is take the mass of the hydrate, subtract the mass of the anhydrous, and everything that's left, because matter is never created nor destroyed, is going to be our water. So we take 6.41 grams, and we subtract 2.83 grams, and we get 3.58 grams. Now we can use this just as our, to find our percent composition of the hydrate, which is basically just asking for the mass, percent by mass of the anhydrous and of the water. And we do this just with our good old formula, part over whole times 100. So for the percent composition of our sodium sulfate, we're going to take the mass of our sodium sulfate over the mass of the hydrate, multiply that times 100, and that should give us our percent composition. So the mass of our sodium sulfate, which is our hydrate, our anhydrous, is going to be 2.83 grams. And our mass of our hydrate, which we calculated up here, is 6.41 grams times 100 equals 44.1%. 3 sig figs, because we had 3 sig figs. 3 sig figs here and here, yes.
I don't know what I pointed to.
It's all of them, it doesn't matter. Okay. And then our percent composition of our water is going to be the mass of our water over the mass of the whole, which is our hydrate, times 100 again. So the mass of our water was 3.58 grams over 6.41 grams, our whole hydrate all together when we started out, times 100. And we are going to get 55.9%. That's a horrible thought. Wow.
I do that to mine too.
55.9%. Now, this tells us that if we look at the mass of our hydrate, right, that's our anhydrous with water, we have 44% of that mass is attributed to our sodium sulfate. But 55.9% of that mass is attributed to water. So a lot of our hydrate is water.
We didn't show you what the hydrates look like, but here's one hydrate. This is one we won't use in lab, but notice that they are solid, right?
They're small crystals.
They're very small crystals, right? Ionic compounds are crystals. This is copper 2 sulfate hydrate.
And this one is our magnesium sulfate. And this is the one we're going to use in the lab. And you can see that these crystals are a little bit bigger. So we're going to determine what the empirical formula is of this one.
All right, that's for next class. Okay, so we've calculated the percent composition of our hydrate. We're now going to look at the last learning target we covered, and that's empirical formula, but specifically for hydrates. Okay, so remember our rhyme for empirical formula. Percent to mass, mass to moles, divide by small, multiply to a whole. We're going to use that here, okay? So, here's our hydrate. We're looking for X. That's ultimately what we're doing to find the empirical formula. This is the empirical formula. We just need to plug in a number here, okay? Now, I've written over there in blue the mass of the anhydrous and the mass of the water, which is what we calculated on the last board. And then I also, because you know how to calculate molar mass already, I've calculated the molar mass of the sodium sulfate and of water, okay? So, first step, percent to mass. Well, are we already in mass? We are. We're in grams. So, skip that step. Percent to mass, mass to moles. That means we need to convert to moles. So, I have 2.83 grams of my anhydrous, Na2SO4. Okay? Now, on the bottom, blue. On the bottom, we need to put the molar mass, grams of Na2SO4, and we've already calculated that up here. 142.05 grams Na2SO4. We're converting to moles. So 1 mole of Na2SO4 goes on top. All right? For the second one, for water, we have to do the same thing. We're starting with 3.58 grams of water. All right? Grams of water, should be able to do this one. Grams of water goes on bottom. Moles of water goes on top. How many moles? 1 mole. What's our molar mass of water? I have it right here, 18.02. All right, and remember, our units cross off. Grams is gone for both of them. So, if we do this calculation, 2.83 divided by 142.05, we get 0.0199 moles of Na2SO4. If we do the calculation on the bottom, we get 0.199 moles of water. All right, so these are almost the same number. They're just off by a tenth, okay? Now, percent to mass, mass to moles, divide by small. Which one's smallest? 0.0199. So we divide both of them by 0.0199. And we get on the top 1 mole of Na2SO4. And we get on the bottom 10 moles of H2O. We've just found X. X is equal to 10. Okay? So if we're going to write the formula, right, for our hydrate, we have Na2SO4 dot 10 H2O. There's our formula. There's our hydrate. All right? Now the name, we've already named this sodium sulfate. Okay? And we need the prefix for 10, which is deca. So decahydrate. Right? Now, maybe I'll write this side, you write that side. We can write the balance equation for this. We're starting with a hydrate. We're starting with the hydrate, sodium sulfate decahydrate, and we're heating it up. So there's our symbol for heat. When we heat it up, it's going to break down into Na2SO4. All right, that's a solid. Huh?
You forgot the...
What did I forget? Oh, sorry. State of matter for our hydrate is a solid. It breaks down into Na2SO4. Solid, and H2O, 10 H2O, sorry, gas. That's it.